Hello students, in today's class we are going to continue the chapter probability. We are going to learn about the axiomatic approach to probability. So far we have learned what is meant by the sample space of a random experiment. First we have seen what is meant by a random experiment, then we have seen how to describe the sample space and the various events of a random experiment, and then we have seen in the last class the different types of events, right? Event equally likely, when the events are called as equally likely, mutually exclusive events, exhaustive events, even A or B, right? Likewise we have seen many types of events. In today's class we are going to see axiomatic approach to probability. What is it? Based on axioms we are going to define the probability of an event. What is meant by axiom? Axiom is the universally accepted truth, right? So based on the definition of the probability, we are going to state three axioms, and in that way, based on those axioms, we are going to give the definition of the probability, and we are going to check whether it satisfies all those axioms or not. Okay, so let S be the sample space of a random experiment. Then the probability P is a real valued function whose domain is the power set of S. A power set of S means what? All the subsets of the sample space, and range is the interval 0 to 1, closed interval 0 to 1. These are all the well-known results which we know right from the lower classes, from when we started learning probability, right? We know the probability of any event will lie in between 0 and 1. If the probability of an impossible event is going to be 0, and the probability of a sure event is going to be 1, and the probability of any event is going to lie in between 0 and 1. All these things we know already, alright? That's why the range is given as the closed interval 0 and 1. So the probability of any event will lie in between 0 and 1, satisfying the following axioms. What are those three axioms? For any event E, probability of that event should be always greater than or equal to 0. Remember, the probability of any event cannot be a negative number. It cannot be less than 0. The probability of any event is always greater than or equal to 0. And probability of S is equal to 1. What is this S? S is the sample space. This only we will call it as a sure event. Probability of the entire sample space is going to be 1. And if E and F are mutually exclusive events, then P of E union F is equals to P of E plus P of F. If E and F are mutually exclusive means what? They do not have any elements in common. If E and F are completely disjoint sets, then their union is nothing but P of E plus P of F. It is simply adding the probability of the two events. These are the three axioms. Alright. First one is probability of any event is greater than or equal to 0. Probability of the sample space is equal to 1. If E and F are mutually exclusive events, then probability of E union F should be equal to P of E plus P of F. Alright. So from this it is clear that probability of the impossible event, probability of the null set should be equal to 0. We have seen all this already, but through this axiom how can we prove this? We are going to take E union F as our empty set. We know any event and the empty set are mutually exclusive event. They do not have any elements in common. So according to this axiom, P of E plus P of phi we can write, right? So P of E union phi is also going to be P of E only, because union with any set with empty set is going to be the actual set only. So P of E is equal to P of E plus P of phi. So P of E will get cancelled. So probability of the empty set is 0. Right? So let S be a sample space containing the outcomes omega 1, omega 2, etc. omega n. This is just a donation, right? Then it follows from the axiomatic definition of probability that these three things you have to remember. These are all the three axioms you have to remember. What is it? Probability of any event will lie in between 0 and 1. 0 less than or equal to probability of omega I is less than or equal to 1. If you choose any element from the sample space, the probability of that particular element. That element is going to be any event, right, which will lies always in between 0 and 1, and it can be equal to 0 and equal to 1. And if you add all the probabilities, it will be equal to 1. This also we know, sum of all the elementary events will be equal to probability of sum of all the elementary events will be equal to 1. Therefore, probability of omega 1 plus elementary event mean what? Singleton element, single sample point of the sample space, right? This also we know already. And also for any event A, P of A is summation probability of omega I, where omega I belongs to A. What does this mean? Suppose any event is a subset of the sample space, right? So if the event has the elements omega 1, omega 2, omega 3, these three elements are there in event A, then probability of the event is nothing but probability of omega 1 plus probability of omega 2 plus probability of omega 3. Those three elements probability, if we find and add, that will give the probability of the entire event. This is the axiomatic definition of the probability. I repeat, what is the first one? Probability of any element, any sample point is lies in between in the closed interval 0 and 1. And if you add the probability of all the elementary events, it will be equal to 1. Then probability of any event is nothing but summation of probability of omega I, where omega I belongs to A, right? Next we are going to see probability of A or B. P of A union B is equal to P of A plus P of B minus P of A intersection B. This is obvious, right? When we have two sets and if they have intersection, if they are not mutually exclusive, then you have to subtract the probability of their intersections, right? This can be proved using Venn diagram also. This is A minus B, this is B minus A, and this is A intersection B. We know already. Now what is A union B? A union B is A union this A union B minus A, right? A union B minus A, right? Where A and B minus A are mutually exclusive. Similarly, B can be written as A intersection B union B minus A, where these two sets are mutually exclusive, right? Now, probability of A union B is equal to probability of A plus probability of B minus A, because we know if two sets are mutually exclusive, then probability of those two sets is nothing but union is nothing but probability of A plus probability of B by the definition itself. Similarly, here these two are mutually exclusive, therefore P of B is P of A intersection B plus P of B minus A. Alright, now we are going to subtract these two equations. So probability of B minus A will get cancelled, and hence we will get P of A union B is equal to P of A plus P of B minus P of A intersection B. This can be proved in this way. If they are mutually exclusive events, then P of A union B is P of A plus P of B. There is no need of intersection. There is a mistake in the book. This is plus. P of A union B is P of A plus P of B. You don't need not to subtract, right? Then what is probability of event not A? Not A means complementary, right? So P of A dash is nothing but 1 minus P of A. P of A dash is 1 minus P of A. So with all these inputs, let us get into the exercise and solve the problems. So far what are all the things we have seen? What is meant by axiomatic approach of probability? The 3 points you have to remember. Probability of any sample point lies in the interval 0 and 1. Then probability, sum of the probabilities of each sample point is equal to 1. And for any event A, probability of that event is equal to summation probability of omega I. And if A and B are any two events, then probability of A union B is P of A plus P of B minus P of A intersection B. Probability of complementary or complement of an event is 1 minus P of A. And if A and B are mutually exclusive events, then P of A union B is P of A plus P of B, right? Now the first question is, which of the following cannot be valid assignment of probabilities for outcomes of the sample space? So they have given you certain assignments. They have given you certain assignments of the probabilities, and they asked you to check which of these are the valid assignment. So how will you check whether the given assignment is valid or not? Two conditions it has to satisfy. First one is the probability of each event should be positive and less than 1, which means it should lie in between the closed interval 0 and 1. It should be positive. First point is it should be positive and it should be less than 1. Second one is sum of all the assignments of the probability should be equal to 1. If it satisfies these two conditions, then the given assignment is valid. So if you see the first question, the probability of all the assignments are greater than 0, which means all are positive and they are less than 1, because 0.1, 0.01, 0.05, 0.03, 0.01, 0.2 and 0.6, everything is less than 1, right? So first condition is satisfied, it is positive and less than 1, right? Second condition is the sum should be equal to 1. So if we add, we are getting 1. Therefore, both the conditions are satisfied. Therefore, the assignment is valid. So this is how only you have to check whether the given assignment is valid or not. Right? So if you see the next question also, you can check in the same way. When it is 1 by 0, 1 by 0 means what? Sorry, 1 by 7. 1 by 7 means which is greater than 1 or less than 1, which is less than 1, right? But and all are positive. Therefore, you can check if we add whether are we getting equal to 1. If you see the D subdivision, few probabilities are negative. Therefore, on seeing that itself, we can say that is invalid assignment. So, to check whether it is a valid or invalid assignment, first you have to check every assignment, every probability of the event should be positive and it should be less than 1. Even if 1 is greater than 1, it is an invalid assignment. Second one, you have to add all the, only if the first condition satisfies, you should check the second condition. You should add all the probabilities and check whether it is equal to 1. If it is equal to 1, then only it is a valid assignment, right? Let us move on to the second question. A coin is tossed twice. What is the probability that at least one tail occurs? When a coin is tossed twice, what will be the sample space? Sample space can be both head, both tail, or head tail, or tail head. This is the sample space of the experiment. Coin is tossed twice, right? Now the event, let A be the, what is the event? Let A be the event of occurrence of at least one tail. What is meant by at least one tail? At least one tail means minimum of one tail. The event should have a minimum of one tail. So in which sample point we have a minimum of one tail? It can be both tail, or it can be head tail, or it can be tail head, right? So all these will come under the event A, because the event A denotes the occurrence of at least one tail. At least one tail means minimum of one tail should be there. There should not be any sample point without any tail. It should have at least one tail. At least it should have one tail. So minimum of one tail it should have. So these three can be the element of event A. Now what is the probability of the event A? Number of favorable outcomes, right? Number of favorable outcomes divided by total number of outcomes. So what is the number of favorable outcomes here? 3 divided by total number of outcomes is 4. N of S. This is N of S. N of S is 4 and here N of A is 3. Therefore P of A is 3 divided by 4, which is less than 1. Right? This is how you need to solve the problem. Hope you got it. See the third question. A die is thrown. Find the probability of the following events. If a die is thrown, what is the sample space? Sample space is 1 to 6, right? Sample space is 1 to 6. 1, 2, 3, 4, 5 and 6. Your first question is find the probability of a prime number will appear. So let A be the event of getting a prime number. So what are all the possibilities? 2, 3, 5. Remember, 1 is neither prime nor composite. Right, so you should not include 1 as a prime number. So 2, 3, 5. So N of A is 3. So what is the probability of A formula? N of A divided by N of S. So 3 divided by 6, which is 1 by 2. So again and again I am repeating, you should get the probability of any event as less than 1. If you get more than 1, what you have done is wrong. You should recheck your answer. Every probability should be less than 1. Right? Likewise, I hope you can do the remaining subdivisions. A number greater than or equal to 3. You should understand what they have asked. Greater than or equal to 3. So it can be 3, 4, 5 and 6. Right? First you have to list out the elements of the event. First list out the elements of the event like I have done here. First list out the elements of the event, then find number of elements and then find the probability. Do step by step. Right? So your probability formula is N of number of events divided number of elements in the event divided by number of elements in the sample space. So first you have to list out, count the number of elements and then go for the probability. Right? Next question is based on cards. So before we get into the problem, I wish to give you the gist of a pack of cards. A deck of cards means 52 cards will be there and there are 4 flowers: hearts, diamond, clubs and spade. Heart and diamond will be red in color, clubs and spade will be black in color, right? Each flower will have how many cards? 13 cards will be there. In each flower there will be 13 cards. And there are 3 face cards. What are those 3 face cards? King, Jack, Queen. So every flower will have 3 face cards. Hearten will have King card, Jack card and Queen card. Diamond will have King, Jack, Queen. Clubs will have King, Jack, Queen. Spade will have King, Jack, Queen. This 13 is inclusive of all these, right? Total number of cards is 13. Out of these 13, 3 will be face cards. So 1 king will be there under hearts, 1 under diamond, 1 under club and 1 under spade likewise. And there will be 1 ace card of each flower. And if you remove all the 4, remaining 10 will be, remaining 9 cards will be there, right? Instead of 1 we will have ace and 2 to 10 we will have numbers, right? So what are those 13 cards? Instead of 1 we will have ace card, then 2 to 10 we will have numbers, then 11, 12, 13 is king, queen and jack, jack, queen and king, right? So likewise we will have 13 cards in each flower. So you should know all these things. The question may be asked like this: what is the probability of getting a red card? Getting a red card means a red card can be of heart or diamond. So the total you have to take 26 red color cards are there. So what is the probability of getting a black card? Means you have to add these two. So what is the probability of getting a king card? There are totally 4 king cards. If the question is what is the probability of getting a black queen card, then how many black queens are there? 2. What is the probability of getting a red jack card? Red jack card, there are only 2. What is the probability of getting a diamond ace? Diamond ace, it is only 1. So only if you know everything, you can answer the question, right? Now let us see the question. Now the question is, a card is selected from a pack of 52 cards. So how many points are there in the sample space? So sample space will have all the 52. So n of s is 52, right? Then second question is, calculate the probability that the card is an ace of spades. So under spade, how many ace will be there? Under each flower, there will be only 1 ace. So ace of spades is 1. So n of a is 1 and n of s is 52. Therefore, p of a is 1 divided by 52. Alright. Next question, calculate the probability that the card is an ace. So how many ace cards are there? Totally 4 ace cards. So 4 divided by 52 is the probability of this. What is the probability of black card? Totally black colored card are 13 plus 13, which is 26. So 26 divided by 52 is the probability of this getting a black card. Right? Hope you got it. Now see the fifth question. A fair coin with 1 marked on one face and 6 on the other and a fair die are both tossed. understand the question properly, only then you can give the sample space. That's why one exercise is completely depicted for writing the sample space. That is very, very important. A fair coin. A coin normally will have two faces. One is tail and the other one is head and the tail, right? Now here, instead of head and tail, a coin marked as 1 on the one face and 6 on the other face, right? And along with the coin, a die is thrown. So find the probability that the sum of the numbers that turn up is 3 and 12. Now how will you give the sample space for this? So when a coin shows 1, the die will have 6 faces, right? So the die can show 1, die can show 2, 3, 4, 5 or 6. So a die can show any one of these 6 numbers when the coin shows 1. Similarly, when the coin shows 6, the die can show any one number among 6. So n of s is 12. Right? Now the question is, what is the probability that the sum is 3? So what is the probability that the sum can be 3? Only 1, 2. Only if 1, 2 appears, it will be 3. Right? So probability of n of a is 1. So probability of the event is 1 divided by 12. Similarly, the next question is, what is the probability of getting the sum as 12? It is only when 6, 6 we will get it as 12. So n of b is 1, therefore p of b is 1 by 12, right? See the 9th question. If 2 by 11 is the probability of an event, what is the probability of the event not A? Not A means, we have learnt, not A means what you have to do. You have to subtract the probability of the event from 1. So 1 minus 2 by 11 will give you the probability of not A. Alright. Hope you can do the remaining problems as homework. So with this, let us wind up today's class. Do question number 1 to 10 as homework from exercise 16.3, and if you have any doubts, you can ask me. Thank you, students.